first one is shown with an arrow pointing up, and the second one is shown with an arrow pointing down. So if I have two electrons present in the orbital, one has a plus 1/2 and the other has a minus 1/2. The plus indicates with the magnetic field direction, the minus indicates in the opposite direction. Okay. So now we have 4 quantum numbers. So I said that if we're speaking about hydrogen and helium, these 3 numbers are the same for both of those. And let's make that case. So here's hydrogen and here's helium. Hydrogen's in row 1, helium's in row 1, correct? That means that n equals 1 and n equals 1. What is the value of L when n equals 1? 0. So L equals 0, L equals 0. What's the value of M sub L when L equals 0?
0.
0. M sub L equals 0, M sub L equals 0. So if I was trying to distinguish between the quantum numbers for helium and for hydrogen, I have no way to do it because they're both the same. So the only distinction is the 4th quantum number, which is the spin. So if we add that into our discussion, we would now say that because this is first, we designate that as a plus 1/2, and this is second, we would designate that as a minus 1/2. So now we have a circumstance where we've made a distinction between those 2 electrons. Even though they're kind of parked in the same orbital, we can still tell the difference because one is a positive 1/2 and one is a negative 1/2. Which leads us to our next rule, and that rule is the Pauli exclusion principle. And the Pauli exclusion principle says every electron has a unique set of 4 quantum numbers, not like anybody else. Its own set of unique quantum numbers. So if I were to describe the 1 electron in hydrogen, its 4 quantum numbers would be n equals 1, L equals 0, M sub L equals 0, M sub S equals plus 1/2. If I were to describe the 2nd electron in helium, it would be n equals 1, L equals 0, M sub L equals 0, M sub S equals minus 1/2. There's the difference that distinguishes one from the other. It's not always this, but it could be that. But they have to all be different. No 2 electrons can have the same 4 numbers, because that would imply that they're the same thing. And that's not allowed. Then we counted them twice, and you know the story goes bad from there. Okay? All right, so let's talk about how many. Let me let that there for a minute. So we're going to talk about the S, P, and D orbitals. So we said that this is L equals 0, right?
Mm-hmm.
Yeah? Okay. And we said that this is L equals 1, and this is L equals 2. So now let's take these and write the M sub L values for L equals 1. What would they be?
Negative 1, 0, 1.
Minus 1, 0, and plus 1. So in the P level, sublevel, we have 3 orbitals. Each orbital can contain 2 electrons. Just like we saw, just like here. That's an orbital that contains 2, no more than 2. So that means in the m sub L equals -1, 0, and +1, where I have 3 orbitals, here I have a total of 6 electrons. So every p sublevel can hold 6 electrons. Let's go down to this one. So for L equals 2, what values of m sub L do we have?
-2, -1, 0.
-1, -2, -1, 0, +1, and +2, which is a total of 5. So 5 orbitals. How many electrons? 10. So as we get into higher and higher atomic number elements, we need to have a higher and higher number of spots for the electrons for those elements to go, or to reside in. So as we continue to build up the number of electrons, they need to have spaces. 2 for the S, 6 for the P's, and 10 for the D's. Now there's also L equals 3, which is F. So how many would that have?
7.
So m sub L here is -3, -2, -1, 0, +1, +2, and +3, for a total of 7 or 14 electrons would be possible. We're stopping here. We're not going to go into the F. So the key here is to remember that for every orbital that I have, or I should say every sublevel that I have 2 electrons in each one of these spaces. Here I happen to have 3 spaces, so I have 2 electrons in each of those. 3 times 2 is 6. Here I have 5 spaces. 5 times 2 is 10, and so on. And this will eventually lead us to the point where we can write the configuration. But we're going to do something a little bit simpler first. And that is looking at looking at how the electrons get their position, or how they occupy the atom as we get into larger and larger elements. So we need to talk about 2, actually a couple definitions, and that is kind of degenerate, shielding, and let's first talk about the term degenerate. So this essentially, for any single electron systems, the obvious example is hydrogen. So any single electron systems have this, all the energy levels have the same amount of energy. That's what the term degenerate means. There's no difference between one level and another. unfortunately, as we add more and more electrons, and we end up with a multi-level system, all the energies are not equal. And they're not equal for potentially one of these two reasons. The term shielding in a multi-electron, this is caused by the interaction between neighboring electrons. So let's take a picture of, we're going to pretend that that's the nucleus. I'm going to put an electron here, and I'm going to put an electron here, and I'm going to put an electron here. We're going to focus on that particular electron. And we're going to draw the same picture. Well, now we have those same three electrons positioned a little bit differently. So in this particular drawing, we have a positive nucleus and we have three electrons, right? So there's going to be some interaction between the nucleus and the electrons. If we focus on this one electron here and that one electron there, what's happening between the nucleus and that one electron? Well, I've got two other ones in its way. So these are essentially providing some shielding or protection from the full positive charge of the nucleus on that one electron. So what that means, we know that opposites attract, right? Positive and negative would attract. So if I've got something else in the way here, this electron is not going to feel the full positive effect of this nucleus. It's going to be shielded slightly. If I take that same picture and now I have all three electrons kind of in the same orbital, each one of those is going to feel the full effect of the positive charge because there's nothing in between them. There's nothing this has something in the way. These have nothing in the way that would prevent it from them from feeling the full positive charge of the positive nucleus. So once we get to multi-electron systems like we would have here, although these are fairly simple, there's interaction between those neighboring electrons that causes some shielding effect, so they don't feel the full positive charge. And we refer to that the net charge that they feel, as the effective nuclear charge. So here, the effective nuclear charge is the full, whatever I have in the nucleus. It might be 3, it might be more than that. It'll feel the full effect, each one of these. Here, it's going to feel less of an effect because it has some electrons that are kind of blocking some of the positive charge for that one particular electron. And that causes the energy levels to not be equal to each other as we get into a higher and higher number of electrons. And so what does that mean? This causes the so the lower the value of L, the lower the energy of that particular level is. Now, the term penetration is kind of the opposite of this. penetration, sometimes the electrons decide they're going to move closer to the nucleus, and the closer they get, the greater the attraction is going to be. So although this may be here, as we get into higher and higher or bigger and bigger elements, some of the levels in those elements actually push themselves further to the nucleus. So they end up being they end up having different energy values from what we would expect them to have. And that's particularly true once we get into the fourth row. And we're going to look at a picture of that in just a moment. I was going to say something else. I don't remember what it was. So let's show you some pictures. Since my drawings aren't that good, let's look at what shielding and penetration look like in a real drawing. So here's a picture of shielding and penetration kind of side by side. Here's the nucleus. Here's an electron that happens to be in a spot where it's having some protection or shielding from the full charge of the nucleus. So instead of feeling this, which is a 3+, instead of feeling the full effect of a positive 3 charge, it only really feels the effect of a positive 1 because these are taking up some of the, is it hard to see? Let me turn the light off.
What are we doing? I think one is on the outside.
Is that better or not? Huh?
Hello.
Yeah, you can see it.
It's definitely outside of it.
There we go.
There we go. So this electron with a positive 3 nucleus, if there was no shielding going on, we would expect it to feel a full positive charge, full positive 3 charge, which means that it would be pulled pretty close to the nucleus. Positive and a -1, that's a bad combination, so it would be pulled very close. However, I happen to have 2 other electrons, which again are moving. They're just positioned, they're positioned in a spot, but we know that they're moving around. They are essentially absorbing some of this positive 3 charge so that this one doesn't feel the full effect of the nucleus. That's a concept of shielding. And in multi-electron systems, that happens without any, it just happens. Now the opposite of that is penetration, where now this electron has positioned itself much closer to the nucleus. So now it has absolutely no help from either of these two. So now it's going to feel the full positive 3 charge from the nucleus because it's much closer. There's nothing in the way to help absorb some of the positive 3 charge. So this phenomenon happens in row 4, and we'll see in period 4, we'll see in just a minute what the impact of that is in terms of how the energy levels are arranged in the atoms. Let me see if I have, I think we can go to the next picture. So the net result of that shielding and that and the penetration is that, remember we said that the principal quantum number increases in energy as we go further and further away from the nucleus. So in terms of how the energy levels in the orbitals are arranged, we always start closest to the nucleus, which is n equals 1. We then move to n equals 2, and in n equals 2 we said that we had P was equal to, L was equal to 1, which means we had 3 orbitals. So we have this is all, we always carry S with us, we have P next, and once we have gotten all of the electrons into the P, then we move to the S. So this is the third energy level. So once again, what were our values for L equals 3? We said that M sub L was -3, -2, -1, 0, +1, and +2. So now once we go from up to here, that's the 3D level. Here's the 3P level, 3S, 3P, 3D. And notice when we get to row 4, things get disordered. Because up to this point in time, we went in a nice orderly fashion from 1S to 2S to 2P to 3S to 3P. And then we would expect to go straight to 3D, but this is in between because of the fact that this level penetrates further into in towards the nucleus and is at a lower energy level than these are. So when we do our electron configurations, it will follow this pattern. And as we get to more and more, as we add more and more electrons, they will take up these spots as we continue up outside and higher number of electrons in the atom. So this is the ordering diagram for multi-electron systems. So let's take a look at helium and hydrogen first. How many electrons does hydrogen have? 1. So we'll put 1 here. How many electrons does helium have? 2. So we're going to put 1 there. So now we have that filled, and if you look at row 1, how many elements do we have in row 1? 2. So when we get to the end here, how many electrons should we have total?
3.
Well, there's only two elements, right?
4.
How many electrons does helium have?
2.
Is at the end of the row, correct?
Right.
Yeah? So how can I have anything more than 2?
Oh, true.
Right? So now I'm at helium. Now I'm going to go to the next row. This is row 2. What's the first element in row 2? How many electrons does lithium have? 3. So I have these 2 plus the third one here. Now I'm going to go to beryllium. How many does it have?
4.
So where's it going to go? It's going to go here, right next door. Because how many electrons can fit in one of these lines?
2.
2. All right, so now we're at beryllium. Who's next?
Boron.
Boron. So where's boron going to go? Oh, we're going to put 1 here. And who's next? Carbon. So here's where it gets a little bit, it always gets a little bit tricky. So these are all at the same energy. Notice they're all on the same line. So the next rule that we need to talk about is called Hund's rule. Hund's rule says that before I put a second one on any of these lines, everybody has to have 1. So what does that mean? If this is boron, the next one for carbon is going to go here. The next one for nitrogen is going to go here. So when I get to nitrogen, I have 1 here, and 1 here. Then what's my next element? Oxygen. Now I come back here because this has to have, if I have to put more electrons in, I have to fill everything before I go to the next step. Oxygen goes here. What's this one? Fluorine. What's this one? Neon. So notice the pattern. When I get to the end of filling that particular row, I'm at the far right of the periodic table. Here, I'm at the far right of the periodic table. There's nothing else there except helium, right? Here, I have these 2 on the left, and I have these 6, which fill up to the right, and now I'm at neon. What happens when I go here? Where do I go after I go to row 2, at the end of row 2? I go to sodium. So now sodium is going to have how many on this line? 1. It only has 1, right? And then I go to magnesium. Where's it going to go? It's going to go here. And then I'm going to go across to aluminum. Aluminum is going to have 1 here. And then what? Who's next?
Silicon.
Silicon, here.
Yeah.
Phosphorus, here. Sulfur, back here. Chlorine here, and argon here, and now where are we? We're at the end of the third row. Now, in the fourth row is where it gets a little weird. Because what's true in the fourth row? So in row 4, come over here with me for a minute. In row 4, n equals 4, what are my values of L? 0, 1, 2, and 3. Right? No, that's not right.
N minus 1.
Yeah, that's right.
Up
Yeah.
to 0.
Wait a minute. Yeah, okay. And m sub L then equals,
No, -3. The same thing as D?
so now I have, so this is the S. Wait a minute, hold on 1 second. N minus 1. Yeah, that's right. Oh yeah, but we're not gonna do F. No, that's not what I wanted. Sorry, I want n equals 3, not n equals 4. So for n equals 3, L is what? 0, 1, and 2? And m sub L is -2, -1, 0, +1, and +2. So this is S, this is P, and this is D. So now let's go back here to our diagram. So we're saying that in n equals 3, which is the third row, it looks like it goes sodium, magnesium, and then all the way across. But according to this, we should have S, P, and D. So there's no D in row 3.
Mhm.
There's nothing there, right? There's no elements in that section. So what happens once I get to row 4 is somehow we have to account for those d electrons, or the electrons that are supposed to reside in the 3d orbitals. So when I go to row 4, what happens in row 4? I have potassium, calcium, and then what? Then I have metals that are kind of in the middle, the transition elements. They're the ones that go back and fill in 3D. So instead of going in a nice orderly fashion like we did down here, we go 4S, back down to 3D, and then back up to 4P. So I get all the way across to zinc. So zinc would be here, and then where do I go? Gallium. So gallium goes back to 4P. So the order gets out of order once we get to row 3 and once we get to row 4 and we're thinking about, well, what about all that other stuff that we kind of left behind?
So the weird spaces are basically the middle
Yeah,
part
the transition elements are the ones that are
and the,
that
are out of order.
that are out of order. So you notice the same thing happens in row 5. So now if I get to the end at krypton and I go now down to rubidium, here's rubidium, here's strontium, and then what do I have? Well, I've got to go to 4D, which now takes care of yttrium and zirconium, et cetera, et cetera, et cetera, until I get all the way across, and then I go back to 5P. So orderly up to here, and then remembering that because we're in n equals 3, I have some d orbitals that get filled after I get to the next row. So we're going to work on some configurations now. Everybody got to picture that in their mind. Okay. on, or is it okay or not?
Turn
Like,
it back on.
huh?
Turn it back on.
Turn it back on?
Can you like welcome back to it?
That's all right.
What's up, sis? You get your hair done? You wanna get the door today?
Hmm?
Did you get your hair done? You wanna get the door today?
Yo, she said the same exact thing.
So we have Pauli exclusion principle. Everybody has to have their own separate numbers. And let's write down the two other rules that we need. So these are the three here are the three rules. First one is Pauli exclusion. And a Pauli exclusion says there are 2 electrons per orbital. And every electron has its own unique set of 4 quantum numbers, where the difference might only be how the electron is positioned, either positive spin or negative spin. Second one, the Aufbau rule. The Aufbau rule says, in terms of how I position, I go from S to P to D to F. So I start here at the lowest, then I go to P, and then I go to D, and then I go to F in that order. So each time I start a new row, I have to start back at S. That's the lowest orbital energy. And then the third rule is Hund's rule. So Hund's rule says that one electron in each orbital before adding a second one in that orbital. Because I like food, I call that the dessert rule. Everybody at the party gets one piece of cake before you get a second. Same deal. Okay, so we're going to work on some ground state configurations of electrons. And we're going to do it first with pictures. All right, so before we put anything in, oh, too much space here. So let's write down our M sub L numbers for each of these lines. So if this is 1s, M sub L here is 0. This is 2s, M sub L is 0. It can't be.
You said that's
Oh,
2?
so
Yeah.
Oh,
Huh?
okay.
Yeah.
Okay.
If it's S, it can't be anything other than 0. How about here? So I have 0 and 1 as my possibilities, right? So -1, 0, and +1. Here, M sub L is still 0, and oops, and here it is -1, 0, and +1. let's do sorry, these are referred to as orbital diagrams. So let's do the orbital diagram for nitrogen. So the first thing we need to do is decide how many electrons do we need to put in the diagram for nitrogen?
7.
7. So according to Aufbau's rule, we start at the lowest first and fill everything that we can before we move up. So how many electrons go here?
2.
2. And we said that one has an up arrow and the other one has a down arrow. So we've taken care of 2. Now we can move up to the next row. How many go here?
2.
2. One this way and one that way. Now we have 4. So our next stop is to go to 2p. All right, before we move there, what element is this at this point?
One, two, three, 4. Beryllium.
Beryllium. Yeah. How many electrons are there? 1, 2, 3, 4. Right? Okay. So now we're at beryllium. Now we're going to go across, and the next element we run into is boron. So how many? We need to put 1 here for boron, right?
Right.
And then we're going to go to carbon. Where does the next one go for carbon? Oh, we have to pay attention to the desert rule.
0.
So the next one's going to go here. That's carbon. Where's the next one going to go? Here.
That's 7.
So now let's take our picture and write the 4 quantum numbers for this electron. What would N be? Yep, 2.
And
Yeah.
this one.
So for this one, N equals 2. What does L equal?
1.
L equals 1. Because it's in P, we know that P has a value of 1, S has a value of 0. So L is 1. What is M sub L?
-1, 0.
It only has one value. Where is it?
1 plus
It's
1.
in plus 1.
Outwards it.
And what is M sub S? Plus 1/2. So those would be the 4 quantum numbers that define the last electron added in nitrogen. So let's do one, we'll do one more. We'll kind of proceed a little bit further. So let's go to fluorine. How many electrons does fluorine have?
9.
9. We already have 7, right? So that means this is all, everybody has 1, so now I can come back, because I have to have 2 in everything before I move to the next row. I can put 1 here, and I can put 1 here. Right? So this is the last electron I add for fluorine. What are the 4 numbers for that one? N equals
2.
2, L equals 1, M sub L equals
0.
0, and M sub S equals negative 1/2. Good. So we'll start here on Monday. We'll do a couple more of these, and then we're going to transition from this to writing the configuration, which is going to eliminate the lines. All we're going to do is take these pieces and write the configuration.
So if we label it plus or minus, are we going off of the arrows? Or
Yep, the arrow. Yeah.
Underneath the -1, landing on that.
No, it goes off the arrow.
So if it was on the -1 with the arrow up, it's gonna be positive?
Yeah,
Okay.
yeah, it depends on how that is. The first one is always positive 1/2. The first one on the line, on every line, is always positive 1/2. Once I put in the second one, it becomes negative, regardless of where it is.
So just to make sure, what you were saying, so basically, if you would have said, like, if the arrow was -1, it would have been, SL would have been -1, but it would have been positive.
Right, yeah. Yeah, so if I'm looking at this one, it would be n equals 2, L equals 1, m sub L equals -1, m sub S equals plus 1/2.
That's what I thought, okay.
So wait, say that, I'm sorry, say that one more time?
So if I'm looking at this electron right here,
Correct.
right? So for that particular electron, n is 2, L is 1, m sub L is,
Minus one.
-1. That means 0. -1, and m sub S is now plus 1/2. Because it's
And L
point-
is 1 because it's P.
Wait, let me finish. That's now positive 1/2 because it's pointing up,
Okay.
right? Right,
And then L is 1 because it's at P,
right,
correct? Okay.
yep.
I'm glad you said it at the end of it all, because I was kind of confused about why that was 0 instead of negative.
Which
The one that
one?
you changed.
Oh,
Yeah.
yeah. Okay, all right, so we'll start there on Monday.
Thanks for asking.
Have a good weekend.
You're welcome.
That's all you know.
That's all I know, yep.